Yes.
Awesome.
All right, yeah, take it away.
Cool. Okay, yeah, so as I mentioned in the questions, a lot of the math I do is kind of inspired by mathematical physics, but in a little different way than people often use that term. So, you know, the way I think of mathematical physics usually is applying math. You know, it's applied math in a lot of ways to solve problems coming from physics. And it's probably more accurate when I talk about what I do to call it physical mathematics, maybe, which is not a term I came up with. I've heard a few people use it. But what I mean by this is the opposite. We're actually using physics, applying physics to solve math problems. And often that's like pure math problems. And in addition to solving math problems, also often generating really interesting conjectures in mathematics. And so the goal, you know, my goal of the talk today is just to give you an example of what that looks like, how physics could be used to solve or generate a problem in pure mathematics. And so the physics that I'm talking about here is going to be string theory, which, and I don't really know much physics. I don't know much string theory, so I apologize if someone does and I'm saying something wrong. But my understanding of the basic setup of string theory, at least one version of it, is that our universe, it's not three-dimensional, it's actually 10-dimensional. And the dimensions are the familiar space dimensions, so there's three-dimensional space that we live in, together with one dimension recording the time. And then there's these 6 extra dimensions, which I'll just call X. And so the question is, what is this X? And, you know, through a lot of complicated physical arguments, the physicists have told us some of the properties that these extra 6 dimensions must have. So it's a 6-dimensional manifold, which means in particular that it's smooth. And what I mean by that is just locally this space X looks like r to the 6. You know, a small region of it looks like r to the 6. And the reason we don't observe it in our day-to-day life is that it's compact and it's very small. And so to give you an idea of what that means, here's a one-dimensional space, which is a line, but maybe this is actually a two-dimensional space. So here the line is r. But if I look at this two-dimensional space, which is r crossed with a circle, S1, you know, it's a tube, but then if I zoom out, so if the circle is really small relative to the length of the line, it just looks like a line. And so maybe these 6 dimensions that we're not seeing are kind of like this circle. Furthermore, so these are getting a little more technical, and this is where the algebraic geometry comes in. This space X has a complex structure, and that means that a small region of it, it doesn't just look like r to the 6, it's a complex manifold, so actually it looks like c to the 3. So 3 copies of c. And then there's this other much more technical condition, which is that it's Calabi-Yau. And all you need to know for that, all I really know about that adjective is just that it means it's flat in some sense. The space X has a flatness property. Okay, and so I'm looking for some manifold X, and a manifold that satisfies all these properties, I'm just gonna, as shorthand, denote it as a CY3, which stands for Calabi-Yau 3-dimensional complex space. Okay. And so, you know, one question coming from physics then is like, what is this space X, you know? And that's kind of a physics question. There's not much, you know, there's no way for a mathematician to answer that. But a mathematical question arising from that is not what is X, but sort of what are all possibilities for X that satisfy all those conditions I mentioned? And this is a geometry question. What are all the spaces which satisfy all those properties? So in the terminology I wrote above, this is just saying what are all of the CY3s, all the Calabi-Yau threefolds. And then if you talk to physicists a little bit more, you might ask this further question, which is that, if I have two different X's which satisfy those properties, how does the difference in their geometry affect the physics or affect the universe we live in? For instance, does some properties of string theory change depending on which X you have? Okay, and so I want to focus on this first question. What are all the possible candidates for X? And see where we can get with that. So the best place to start is not with three-dimensional stuff, which is pretty hard to visualize. 3 complex dimensions is a 6-dimensional space. But let's start in 1 complex dimension, which means 2 real dimensions. And so look at surfaces. So what are surfaces which satisfy these properties of being flat in some sense, compact, etc., having a complex structure? So 1-dimensional complex manifolds that are compact with complex structure, some of you might know, these are given by Riemann surfaces. And topologically, a Riemann surface is characterized by how many holes it has. And so I can kind of write down all the possibilities in 1 dimension for compact complex manifolds, etc. Okay, and so these are what they look like. And then there's that mysterious Calabi-Yau property that I mentioned, which is really just some flatness property. And the flat one out of all of these is the torus. And of course, it doesn't look flat the way I've drawn it, but that's because I've only drawn topologically what it looks like. The way I put a complex structure on this torus, think of it as something that locally looks like C, is I take the complex plane, I cut some parallelogram out of it, and I glue edges together. So I glue the top and the bottom, and I glue the left and the right sides. And you can see that this object, in some sense, is flat because a small region of it just looks like C, and C is a flat plane, right? And so in 1 dimension, this is the only compact Calabi-Yau. So that's at least a starting place. In 3 dimensions, it becomes much more difficult because there's more than one. There's many, many, many. Like a truly massive number. And so to classify all Calabi-Yau threefolds is, it seems overwhelming. And so a first step is try to find some invariants of these things and classify maybe which invariants can occur. And so a first step towards thinking about what invariants we can consider is discrete things. And you can talk about homology groups, Betti numbers, Hodge numbers. There's many different variations of this, but really what I'm talking about in some sense is the number of holes in your space of different dimensions. And so let's look at the torus as an example. So this has holes of 0 dimensions, 1 dimension, and 2 dimensions. The 0-dimensional hole, we're really just meaning the number of connected components. So it has 1 0-dimensional hole. By which I mean it just has 1 connected component. And then up to some sort of deformation, there's exactly two one-dimensional holes. And I mean by that, like something that's one-dimensional, so it locally looks like a line that encloses some two-dimensional space. And so there's this green circle and there's this purple circle. So there's two one-dimensional holes on this space. So these are coming from closed loops is really what I'm counting there. And then the two-dimensional hole is a surface which is enclosing some volume. And there's really one of those, which is the torus itself. Okay, and so I've got these numbers, 1, 2, 1, which is telling me something about the shape of my space. I'm gonna refine this, make it just a little more fancy, using the complex structure. So if you take into account the fact that this torus is a complex manifold, you can group these numbers in a fancier way, and this is called Hodge numbers, but it doesn't matter too much. Basically, the zero-dimensional holes are these, two-dimensional holes are these, and I'm going to group the two one-dimensional holes in a specific way, and I get this diamond where the row is the dimension of the hole. So the zeroth row is this. The second row is the two one-dimensional holes. The third row is the two-dimensional hole. And you can do this for any manifold, and this is, this is some way of organizing some discrete data. And so for the rest of the talk, I'm going to look at this kind of discrete data for three-dimensional Calabi-Yau manifolds. So what about in 3 dimensions? So remember, this is 6 real dimensions, 3 complex dimensions. So you have 0-dimensional holes all the way up to 6-dimensional holes. And the Hodge diamond is a little more complicated. It doesn't matter too much, but there's these, whatever, I guess 16 different numbers we get, where again, the row is the dimension of the hole, and we're breaking those up in some certain way. So this is the Hodge diamond of a complex 6-dimensional manifold. And some algebraic topology tells us that if we have this Calabi-Yau condition, then a lot of these numbers are determined already. So the Hodge diamond ends up looking like this. The outside is fully determined. We're always going to be connected. So there's one 0-dimensional hole, one 6-dimensional hole. There's no 1-dimensional holes. There's some number of 2-dimensional holes. That's a parameter that can change depending on x. And the 3-dimensional holes, I split up this way, but these two numbers are the same. And so it really reduces to just these two numbers. So this is the 2-dimensional holes, which is also the number of 4-dimensional holes. And this B is basically telling us the number of 3-dimensional holes in this 6-dimensional space. Okay. And all the other speakers have given such great pictures. So I pulled this off of Wikipedia. This is a slice of a particular example of a Calabi-Yau threefold. So one of these x's that could be the extra dimensions of our universe. And for this one, A is equal to 1 and B is equal to 101 for what it's worth. Okay. And so a first step, if we're trying to classify all such Calabi-Yau threefolds, could just be to ask the question, what are the pairs of A and B that can occur, right? So what are the possible A comma B pairs, counting the number of holes? And an idea from physics, which I wouldn't have necessarily thought of, is just to start, take the spaces we know are Calabi-Yau threefolds and just start graphing A and B and see what pops up, see if any patterns emerge. And so here's a graph. It turns out to be convenient to organize things slightly differently. So the horizontal axis is actually a minus b times 2, and the vertical axis is a plus b. But you can recover a and b from that, so it's the same info. And so this is a graph for basically the simplest Calabi-Yau threefolds, the ones that are easiest to write down. And if you sort of expand this out, there's about 8,000 data points here. So 8,000 different spaces. And if you're looking at this, you might make some conjectures. Like it seems that there are some patterns here. Everything's kind of clumped in this one small region, right? So you can start to guess some things. The first question is like, is there an upper bound? Can we not go too high if we look at a plus b? And, the second kind of thing that stands out here is b always larger than a, which is why a minus b in this graph is always negative. And, that's an interesting idea. Maybe the number of three-dimensional holes is always larger than the number of two-dimensional holes. It's not obvious, but maybe it's true. But there's a concern here, which is that maybe it's not. Maybe that's not a good conjecture. Maybe it's not coming from some constraints put on this space X. Maybe it's just an artifact of the specific ones we're looking at. How we're constructing these. But you can make a guess. And so, the next thing to do, for lack of a better idea, is just to start graphing more. Come up with other classes of Calabi-Yau threefolds, see what the A and the B look like. So in the 1990s, largely started by someone named Candelas, they started looking at other types of Calabi-Yau threefolds. And I should say the class up here, for those of you that know the word, these are all ones that live in projective space in a particularly simple way. Candelas generalized this just slightly by looking at Calabi-Yau threefolds inside weighted projective space. And so here's the graph that Candelas got, which looks quite different from the one we saw before. So looking at weighted projective spaces, we get 7,555 data points. And you see that one of these conjectures was wrong, because for a lot of these we're on the first quadrant of the graph, which means that A is larger than B in a lot of these examples. So the first conjecture turned out to not really hold when we looked at more data. But here there's again a lot of pattern to the data. And so again, we may want to look at this and come up with some conjectures. And the most tantalizing thing about this particular graph is this symmetry that it has. The left side looks exactly like the right side. And so let's think about what that means. So basically, for some point here, there's in not every case, but in a lot of them, there's a corresponding one on the other side of the y-axis, right? And so what this means is that for a lot of these pairs A comma B, there's a corresponding pair A prime B prime where they're at the same height. So A plus B is A prime plus B prime. And their distance from the y-axis is the same. They're just one's positive, one's negative. And so A minus B is the negative of A prime minus B prime. And so you solve these equations, and what you see is that the relation between these pairs is that A is equal to B prime and B is equal to A prime. Okay. And so this is the conjecture. It's called Mir symmetry, because if you put a mirror here, the picture looks the same. So this is a conjecture coming from physics, which is that for each of these pairs, A comma B, arising as the number of 2- and 3-dimensional holes of a Calabi-Yau threefold, for some space M, there's another space, another example Calabi-Yau threefold, which I'll call M check, that has the exact opposite A comma B. So A is B and B is A for this new space. And so each of these candidate spaces for our universe M, it has a partner, M check, where these invariants are kind of switched somehow. And the M check here is often called the Mir manifold of M. It's the one that makes this Mir symmetry happen. Okay, so that's the conjecture. But again, you could ask, or is this just because of how we chose our Calabi-Yau threefolds? Is it just because we looked at certain specific ones? Well, the first thing I would say is, like, even if it is, it's already pretty interesting that all the Calabi-Yau threefolds of a certain type have this weird symmetry. But it'd be more interesting if this pattern persisted. So let's add more. So people started doing this. They started generalizing ways of constructing these, and most of these came from toric geometry, these new examples. And so this next graph is adding quite a few more examples. And so here, this is actually a heat map, because there's too many just to plot with dots of, so I wrote this down, 473,800,652 different examples of candidate spaces for our universe, which satisfy the Calabi-Yau property. And we notice that the symmetry really seems to be persisting. There's the y-axis, you flip these, it looks exactly the same. And so there must be something to this. And there's some other interesting conjectures that you can make as well. Like it's really seeming like the pairs A comma B are lying inside a certain region. So, like, what's the deal with these bounds here? I actually don't know the answer to that, although there is a math overflow question about this that I didn't understand, that people seem to know why that is. But it's not obvious that there would be these constraints. So people can continue generating more and more examples. And just for people that are interested in big data, the current database of all Calabi-Yau threefolds, so all possible candidates for our universe, is around 10 to the 10 distinct examples. This paper I was reading said it's perhaps the largest data set in pure math. I don't know if that's true, but that would be kind of cool. And so there's this symmetry, right? And so there's this question about what's going on with this symmetry. And it turns out it's really just the tip of the iceberg. So what we've been looking at are Hodge numbers, these A and B's, but there's actually a lot of stuff that's a lot of invariance much deeper than just counting the number of holes, where this symmetry also happens. And so there's refined versions of the Mir symmetry conjecture, which again is based on this fundamental idea that for any one of these candidates for our universe, this M, if you look at its invariance, there's some other space, M check, that has the same invariance up to some switching. And so, for instance, the number of two-dimensional holes of A is related to the number of three-dimensional holes. Sorry, the number of two-dimensional holes of M is related to the number of three-dimensional holes of M check, and vice versa. So the A over here equals the B over here. But then you start getting deeper. So actually, the number of two-dimensional holes is related to the symplectic geometry of this space M. So the kind of stuff that Clay studies, for instance. And the B here is related to the complex geometry, complex analysis of this other space. And so something really deep is going on here, where the symplectic geometry of one space should be isomorphic in some complex way to the complex geometry of a totally different space. And you can keep going. So there's, at this point, there's many sort of manifestations of this phenomenon. And it's been checked in a lot of examples. So one is if you look at the number of curves in M, and by curves, I mean complex curves, so Riemann surfaces inside of M. One really interesting thing about these constraints of being a Calabi-Yau threefold is it's expected that in a lot of cases, the number of Riemann surfaces that sit inside one of these spaces is actually finite. And so you can count how many curves are there of a given genus and sitting inside it in a certain way. And you can get those numbers. I put a star here because that's actually where the algebraic geometry comes into this story most directly. Counting the number of curves inside of one of these algebraic spaces is a really old question, actually. It's something that algebraic geometers have tried to solve and have successfully solved in a lot of cases for hundreds of years. It goes, it connects to the Schubert calculus that Maria's into, which is from over 100 years ago. But it's a pure algebraic geometry question, and it's quite a hard question. And what the Mir symmetry conjecture coming from physics predicts is that if I look at this other space M check, then somehow in a complicated way, the number of curves in M should be related to what are called period integrals of M check. And you don't need to know what period integrals are, but the point is it's a rather classical subject, which actually we have a lot of techniques for solving. And so one cool application of Mir symmetry is I can answer algebraic geometry questions over here by doing integrals, which I know how to do, on an entirely different space. And so this is a way of, if you're a physicist, you know this to be true. They have some physical reasons for this Mir symmetry, but mathematically we can do these integrals and get conjectures for the number of curves in a different space. And it continues. So the Lagrangian submanifolds of M should correspond to vector bundles of M check. And there's really just a million different manifestations of this conjecture at this point. So a few questions coming out of this is, of course, if you just give me a Calabi-Yau threefold, one of these spaces, how do I find its Mir partner? Because if I want to apply this duality here and actually use it, I need to know what M check is. And toric geometry is one of the great tools for doing this. And then another natural question is, this symmetry that we have, does it hold for other classes of spaces? So what about things in other dimensions, like the torus that we looked at? What about if I remove this flatness condition and just look at random complex manifolds? And it turns out that for these two, there is a version of Mir symmetry. So the same symmetry actually does occur for general complex manifolds. But interestingly enough, the Mir, the M check, is often not itself a geometric space in a way that we're used to. So we have to expand our notion of what a geometric space is. So often the Mir to a manifold is an orbifold or a stack. And this is something that's like a geometric space, but it also has a group acting on it. And so you end up getting into representation theory that way, or even more general things. And then finally, one question that I'm particularly interested in is, so we've got like trillions, maybe not trillions, but at least billions of candidate spaces for our universe. So one question is, does it really matter which one we choose? So if I change the geometry of my space M from 1M to some other, how does it affect different invariants that the physicists care about? And so how does it affect, for instance, these things like the number of curves or the number of submanifolds of a certain type? So those are really the questions I'm interested in. And the physicists have a lot of conjectures, which is really useful for us mathematicians. Even if we have to prove them rigorously mathematically, oftentimes having a guess of what the correct answer should be allows us to prove things, right? Like if someone tells you this is an antiderivative, then you can easily check if they're right or not. But finding an antiderivative of a function on its own is sometimes a difficult problem. And so the same thing like that, often the physicists give us candidates to check, and then we just have to prove it. So I think I'll stop there. Thank you.